All right, I wanted to kind of quickly summarize for the benefit of those who have maybe missed a class or two. And what we have introduced, I won't do this necessarily in exactly the same order as some notation for area under a curve. And that the notation kind of looks like this. If we write, say, a to b, this is called the definite integral from a to b, area underneath the curve of a function with respect to x. What we are interpreting this as, I'll draw an arrow, it's not equal, not being very precise here, is that we have some function. Some function. And we have an interval from a to b, and the area under the curve, that is, when we say area under the curve, we mean the area under the curve and above the x-axis. So we have this notation, which means this area underneath here. So here's sort of a algebraic notation and a geometric interpretation. And what we did with this is we said, okay, well, we can actually make an estimate of this by taking rectangles. For example, if we break this up into 1, 2, 3, 4 intervals, we can use the right end point or left and make some rectangles. Right end point up to the function over, boop. Right end point up to the function over, right end point up to the function over. And if you look at these carefully, notice some of the rectangles are overestimates and some of them are underestimates. But you know, this gives us an estimated area, and these were called Riemann sums. And we use rectangles because rectangles are easy to calculate. The area of a rectangle is equal to the width times height. The width is a delta x, or a dx, and the height is f of x. So I got them in reverse order. Hence we see that the area underneath the curve is equal to, we're sort of adding up all the heights and the widths. Whereas dx, as it did with derivatives, meant that it went to 0, that the delta x shrunk down to 0. The more rectangles we take, the better the estimate. Okay. Now, I'm going to write down a somewhat more complicated statement for that. I'm going to use that same notation. So what we said is that the area, or the definite integral from a to b of f of x dx, is approximately equal to the sum, oops, not n, scribble, 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 k equals 1 to say n. It's equal to the sum of n of these rectangles, where we have f, the height of each rectangle is equal to f of a plus k delta x's, and the width is equal to delta x. So this is sort of a formulation, an algebraic formulation of this. That is to say, we're going to add up, in this case 4, we can add up 100 or 1,000,000 rectangles, and this is a formula for calculating that. We kind of went over that in class, so you may come ask about that or peruse some notes, or maybe I'll make another video trying to clarify where that comes from. So lastly, for now, we can say the following. The definite integral, I'll try to leave this previous statement on the page. Here's the idea here. The definite integral, or the area under the curve of f of x dx, is exactly equal to, up here it's approximately equal to, because no matter how big we make n, it's still just going to be an approximation. But if we take the limit as either n goes to infinity, or equivalently, delta x goes to 0, those are interchangeable, like those Christmas colors, of this whole expression. I'm just going to transcribe this whole thing here. We're going to take the limit as n goes to infinity of k equals 1 to n of f of a plus k delta x's times delta x. If we take an infinite number of rectangles, slowly scroll back up here. If we take an infinite number of these rectangles, that is to say, if we let the rectangle shrink down to 0 width, we'll get an exact area. But anything less than infinity gives us an approximate area. This is kind of an unwieldy statement, but it sort of captures the essence of Riemann sums in a pretty cool looking equation. You write that in your notes, people think you know what you're talking about.